Hey guys, Mr. Fawcett here, and we are back with another AP Calc AB lesson. Today we're going to look at determining limits analytically, and we're going to specifically look at vertical asymptotes. The second part of this lesson, using conjugates, will be a part 2. I'm not going to try to squeeze everything in. The vertical asymptotes part is, I think, a little bit easier to understand and algebraically easier than using conjugates, so we'll just kind of break those up. First question that I want you to think about is trying to use what we learned in our previous lesson to find this limit below. So lesson 1.5 dealt with us using direct substitution, which sometimes led to just finding the limit right away as long as our function was continuous, but sometimes it led us to an indeterminate form, and then we had to do some factoring and simplifying and then some more substitution to figure out what the limit actually was. So I want you to kind of run through those processes and see if it leads you anywhere. Take a couple minutes and then just compare it to the work that I'm about to do. Okay, hopefully you've had time to work through it. So let's just see what happens when we use some direct substitution. Again, we're going to take the limits of our numerator and denominator separately. If you use direct substitution here, you're going to end up getting 20. And my limit of the denominator will end up being 0. So we know that our function is discontinuous at 2 because our denominator is equal to 0. However, we don't have an indeterminate form, right? Because an indeterminate form, the form that we looked at, was 0 over 0, or 0 in the numerator and 0 in the denominator. So we don't have an indeterminate form, but maybe some factoring will help us out. So let's try that. If I factor this, again, I'm going to keep my limit notation. And I'm going to get the quantity x plus 3 times the quantity x plus 2 over the quantity x minus 2. Again, we're running into a bit of a problem because we don't have any factors that simplify. So again, we already know this is discontinuous. If we substitute in 2, we end up getting 0 for our denominator, so we're not going to get an actual real number answer for our limit. And we can't simplify any factors. So maybe we have to think back a couple lessons further. If you ran into this problem, how could we still evaluate this limit? Do we have any tools in our toolbox left to try to come up with an answer here? Take a couple minutes to think about it, and then we'll talk about some possible solutions. Okay, so hopefully you thought back to using either a table or a graph. I'm going to pull up my TI-84 software, and we're going to check out both, actually. Let me first get rid of this stuff. So I'm entering the function. Okay, functions entered in y1. We are looking for the limit as x approaches 2, so I'm going to start with the table. And I'm going to go again to the little, this is already set up from a previous lesson, but I'm going to start at 1.997 and increase by 1,000th every time. I'm going to look at my table, and something different seems to be occurring here. So I'm just going to block off 3 x values on either side. We know that there's an error when we get to 2, but we knew that the function was discontinuous there, and that doesn't really matter. As we get closer to 2 from the left, our numbers go from negative 6,600 to negative 9,900 to almost negative 20,000. So think about what those numbers are approaching. Are they increasing? Are they decreasing? Are they getting closer to a specific number? And then as we get closer to 2 from the positive side, again, we go from about 6,600 to 10,000 to 20,000. These numbers don't seem to be approaching any real number. As we approach from this side, right, we seem to be getting closer to negative infinity. As we approach from this side, we seem to be getting closer to positive infinity. And again, infinity is not a real number, it's an idea. So these functions are, you can call it increasing without bound. One is getting closer to infinity in the negative direction, one is getting closer to infinity in the positive direction. So right away, we should be able to say limit does not exist, right? Unless we're going to start talking about infinite limits, we would say that the limit does not exist. Let's take a quick look at the graph though, just to show you, give you another visual about what's going on. I need to reset my zoom. And let's zoom out a bit actually. Okay, that's a little bit easier to see. So as we approach 2 from the negative side, right, we come up, and then we're just shooting down. As we approach it from the positive side, we come down, then we're just shooting straight up. And there's an asymptote there. It's not drawn in, but if we wanted to, we could kind of show you. Right, asymptote at x equals 2. So the function's increasing as you approach from the right. It's to infinity. It's decreasing as you approach from the left. So hopefully you would take advantage of these tools. Again, this is kind of our old school way of doing it right now. We haven't really learned another way to understand. Well, actually, I take that back. We are going to talk about things you learned in pre-calc to help you out with this. But as far as what we've learned in calc, you would need to use a table or a graph to figure out this limits question at the time being. But again, this lesson is going to lead us into something what's going to be a little bit easier for you. Let's get rid of this. Let's go back to our notes. So basically the takeaway of what we just saw in the calculator is that if we have a function that has a vertical asymptote, right, if we go back to our calculator real quick, we saw that there was a vertical asymptote at x equals 2, which is the x value for the limit that we were talking about. If there's a vertical asymptote, then the limit technically will not exist. Okay, again, we'll talk about what we call these infinite limits a bit later, but the technical answer is if you can identify that there's a vertical asymptote at the point where they're asking about a limit, you can just say the limit does not exist. Okay. We may need to review how to figure out where those vertical asymptotes are though, which is what we're going to do now. So vertical asymptotes, these occur when the factors in the denominator cannot all be simplified out with the common factors in the numerator. So essentially, if we can get a function, or if we can get a fraction where we have a real number in the numerator other than 0. So if we can get something like L over 0, where L is a non-zero real number, then we will have a vertical asymptote somewhere. We still have to figure out where it is, but we know that it will occur. It's actually going to occur at the x value that made the denominator equal to 0, right? So if we have, let's say, we're going to do this more complicated one in a second, but let's say we have f of x. You know what, let's use something else because I already have f of x on the screen. Let's use g of x. So if I have a function g of x is equal to 3 over, well, let's just do an easy one, 3 over x. There's an x value, namely 0, where I would have 3 over 0. So again, g of 0 is equal to 3 over 0, which is actually undefined. But we would have a vertical asymptote at x equals 0, because we have a real number in the numerator, 3, that's not 0, and we have 0 in the denominator. Likewise, let's say I guess we'll do it side by side. Let's say I had h of x was equal to 4 over x plus 5, right? Well, there's a number that makes the denominator equal to 0, right? If I do h of negative 5, that's going to give me 4 over 0, which fits the criteria for a vertical asymptote. So I'd have a vertical asymptote at x equals negative 5. So again, hopefully this is a little review from Algebra 2 and Pre-Calc, where if you can figure out where the denominator is equal to 0, as long as the numerator also isn't equal to 0, you're going to have a vertical asymptote at whatever that x value was. Okay, the thing that we're going to work towards right now is that we're going to have to do some factoring to get there. They're not going to be as easy as the purple and the red examples. So let me erase this and we'll get started on something a little bit more, not too much harder. It still is within the Algebra 2 realm. So if I have a function right here and I'm just being asked to find the vertical asymptotes, I need to see where the function's denominator is equal to 0, but the numerator also can't be equal to 0. So the easiest way to do that is just to factor. It's going to be easy to factor this denominator, so that's what I'm going to do first. Just GCF, I get 6 times the quantity x plus 4. Factor in our numerator. I need 2 factors of negative 72 that add to 14. So we're going to have x plus 18 times the quantity x minus 4. Now, if there were 2 factors that simplified, we would simplify those out because those would then not be a vertical asymptote. If we think back to last lesson, if we have 2 factors that simplify, there's actually going to be a removable discontinuity there, not a vertical asymptote. So if nothing simplifies, all we have to do is look at the denominator, right? And we need to see where is that denominator equal to 0. Well, 6 is never going to be equal to 0, regardless of what x is, because 6 is always going to be 6. But we do have this factor. So x plus 4 is equal to 0 when x is equal to negative 4. Okay, and you could check, but it's probably pretty trivial to notice that when x is equal to negative 4, our numerator up here is going to be some number other than 0. You don't have to know what it is. You just have to know that's not going to be equal to 0. So we have a vertical asymptote at x equals negative 4. Hopefully, again, this is just all review still, but it is something we need to know. So again, if they were asking you for what's the limit of this function as x approaches negative 4, well, if we know that there's a vertical asymptote there, we would know that the limit does not exist, right? Because the function's going to be either approaching positive infinity or negative infinity, depending on what side we're coming in from. So, and I'll just write this down. This just kind of leads into our next discussion. It's going to be the limit as x approaches negative 4. I'm going to have to write this all out. So minus sign over 6, 6x plus 24. And this would be d and d. So again, they would most likely give you a question that looks something like this. And you could use your knowledge of vertical asymptotes to just know that the limit does not exist. You wouldn't have to go through all the steps of writing out a table or etc. Or graph or whatnot. If you could figure out that there was a vertical asymptote there, D and D would be your correct answer. Unless they wanted you to be more specific and use infinite limits, then you'd have to figure out whether it was going to positive infinity or negative infinity. But that's for another time. Okay, let's look right here, and this kind of goes right along with what I was just saying. For now, it will be enough to be able to identify whether a rational function has a vertical asymptote at the x value for which the limit is asking about. If it does, then you can write DND or unbounded. We're going to go with DND for now, does not exist. We will go more in depth with vertical asymptotes and infinite limits in later lessons. So I want to go through one example with you guys before I let you practice on your own. And I want you to be careful in this section because I may not just be talking about vertical asymptotes, right? You may just be able to use direct substitution, or you may be able to use some factoring because there's a removable discontinuity. So we're at the point where you're going to have to start building on what we've learned before and not just incorporating the new stuff we've learned in this lesson. So let's actually look at number 4, and then you guys can work on the others on your own. Okay, so when you're trying to evaluate a limit, the first thing you need to do is, or the first thing that makes the most sense in terms of making it easier for you, is to try substitution. Okay, so you want to substitute in to the numerator and you want to substitute in the denominator. And even if you know that that's not going to give you an actual answer because you can already tell that the function's discontinuous at that point, it's going to give you a better understanding of where you need to go next. So maybe you'll figure out that it's an indeterminate form. Maybe you'll figure out that there's a vertical asymptote. So direct substitution is kind of our first path that we need to traverse, and maybe it leads us to another path down in the future, but it's one where we should start. So we're going to start with the numerator. So the limit as x approaches -2 of x squared plus 11x plus 18. And again, you can punch this into your calculator, but this is going to give us 0. Okay, we get 4 minus 22 is -18 plus 18 is 0. I'm going to do the same thing for my denominator. X squared plus 8x plus 12. And again, this is also going to give us 0. We're going to get 4 minus 16, which is -12, plus 12, which is 0. So these getting 0 in both our numerator and our denominator when substituting gives us an indeterminate form. Now, if we think back to our last lesson, this means that we're not done. It means that the limit may exist. We just have to keep going to try to find it. So again, what we've learned from our previous lesson for removable discontinuities is we're going to try to factor. So I'm going to need to factor both the numerator and the denominator. You guys may have more space here. I'm actually going to clear this so I have more room to work. This is just simple trinomial factoring. I'm going to get the quantity x plus 9 times the quantity x plus 2. And then in my denominator, I'm going to get the quantity x plus 6 times the quantity x plus 2. And right away, we notice that we have two factors that we can simplify, right? So we can simplify those, and this will give us a better limit expression to work with. We just get the quantity x plus 9 over the quantity x plus 6. And now we can actually apply our direct substitution and be confident that when we get a number, that's going to be our actual answer. Remember, the function doesn't have to be continuous everywhere for us to be able to use direct substitution. It just has to be continuous at x equals a. And in this case, our x equals a is x equals -2. So even though this function is discontinuous at x equals -6, that is not the value we care about, right? It's continuous at x equals -2, which means we can use direct substitution and use whatever answer we get as our answer to this limit. So we get x, not -7, +7. So we get 7, One more time. 7/4. So the answer to this limit would be 7/4. Note that this was not a vertical asymptote. This was a removable discontinuity. This would be like having a hole in the graph, right? So think about all the tools you have in your toolbox right now. And don't just think that, oh, we're in the section of vertical asymptote, so I'm always going to get a vertical asymptote. No, we expect you to build on what we've learned previously. So you could get, you may not have any discontinuities. You may have a removable discontinuity, or you may have an infinite discontinuity, a vertical asymptote. Okay, so you can try these other ones on your own, and I will see you back for the second part of this lesson where we talk about using conjugates. All right, this is Mr. Fawcett. Enjoy the rest of your day.